This is 11.6, absolute convergence and the ratio and root test. So the definition of an absolutely convergent is if the series is absolutely convergent if the absolute value of a sub n is convergent. And it's conditionally convergent if only this series is convergent but not the absolute value. And if it's absolutely convergent, then it must be convergent as well. So let's look at the first example. They want us to determine whether it's absolutely convergent or conditionally convergent. Well, we can tell that it's not absolutely convergent because if you were to take the absolute value is simply going to be 1 over radical n. And this is divergent by the p-series with p equal to 1/2. So it's not absolutely convergent. So let's check to see if it's conditionally convergent. And we can check by the alternating series test. Let b sub n equal 1 over square root of n. We know that b sub n is decreasing. All right, now we just need to check the limit as n approaches infinity of 1 over radical n, which is clearly 0. Thus, the series is conditionally convergent. All right, this next example, let's first check to see if it's absolutely convergent. That's what you should normally do. You should check to see if it's absolutely convergent first. If it's not, then check to see if it's conditionally convergent. So let's check to see if you were to take the absolute value, you're going to get 1 over n cubed plus 1, which is less than 1 over n cubed. All right, and since 1 over n cubed is convergent, it's a p-series with p equal to 3. That makes it convergent. Then the series must also converge by the comparison test. So it is absolutely convergent because we first we took the absolute value of this and we got this, and then that's less than this. This is convergent, therefore this must be convergent by the comparison test. All right, let's move on. So now we have the ratio test. The ratio test is nice. You will take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. And if the limit is less than 1, then we say it's absolutely convergent and therefore convergent. If it's greater than 1, then or infinity, then it's divergent. If it's equal to 1, then the test is inconclusive and you have to try some other test. So for this first example, we're going to apply the ratio test. So we're going to take the limit n approaches infinity, absolute value of n plus 1 over n plus 1 squared times divided by a sub n, which is also the same thing as multiplying by the reciprocal, n squared, negative 2 to the n. So I'm doing this ratio here, but instead of dividing, I'm multiplying by the reciprocal because it's going to allow me to cancel things out. I can rewrite this in this form. All right, so I broke this up into two separate terms, the negative 2 to the n and the negative 2 to the 1. All right, and now I'm going to be able to cancel certain things out. I'm going to be able to cancel these two things out. The absolute value of negative 2 is positive 2, so I'm going to bring the 2 out. So that just becomes 2 on the outside. The absolute value allowed me to do that. And now I just have, since n are positive values, you don't need the absolute value signs anymore because n is approaching infinity and it's going from 1 to infinity. So all these n's are positive. So you really don't need the absolute value at this point. And then if you divide by n squared, you're going to get 1 over 1 plus 1 over n squared. This will be 0, and so we do get 2 times 1, which is 2, which is greater than 1. And if it's greater than 1, the conclusion is that it is divergent. Divergent by ratio test. All right, the next one, let's do the same thing. The limit as n approaches infinity of the absolute value of n plus 1 divided by a sub n, which is, I'm just multiplying by the reciprocal again. So we can rewrite this factorial to be n plus 1 times n factorial. That's how you can rewrite this factorial to be that. And the reason I'm doing it this way is so that I can cancel out the n factorials. And same thing, I'm going to break this up into two different two different terms. So that's 100 to the n times 100. And now I can cancel these. And as you can see, as n approaches infinity, since n plus 1 is in the numerator, this is just going to approach infinity. So this is going to approach infinity, which tells us that if it approaches infinity, then it's divergent. So divergent by the ratio test. All right. So far, both of these have been divergent. Let's look at the root test now. The root test is when you take the limit of the nth root of the absolute value of a sub n, and the same applies. If it's less than 1, it's convergent. If it's greater than 1, it's divergent. If it's equal to 1, it's inconclusive. So in this case, you can see that both of them are raised to the nth power. That's kind of the giveaway that should tell you that you should apply the root test when both of the terms are raised to the nth power. So let's do that. The limit as n approaches infinity, the nth root, absolute value of negative 2 to the nth over n to the n. Okay, so when you take the nth root of n, they cancel, and this comes out as a positive 2 because of the absolute value. So it's going to be positive 2, which I can write on the outside. And this is going to be that n and the nth root are going to cancel, and you're just going to get n. And this clearly approaches 0, and that's less than 1. And if it's less than 1, the conclusion is that it's absolutely convergent, which also means that it's convergent by the root test. All right, let's do the same thing for this one. Notice that it's also, the entire term is raised to the 5nth power. That should be the clue that you should be using the root test. So let's go ahead and take the nth root of the absolute value of negative 2 and over n plus 1 to the 5nth. All right, so let's see here. So you can think of the nth root as 1 over n. So imagine this whole thing to the 1 over nth. The n's are going to cancel, and you're just going to have 5 to this, but because of the absolute value, this becomes positive 2. So this essentially becomes 2 to the 5th, which is 32, and then you're going to have 1 over n plus 1 to the 5th power. So this comes out as n plus 1 to the 5th because of the 5. The n's cancel each other out. The absolute value turns this negative 2 into a positive 2. 2 to the 5th is 32. And this is clearly going to go to 0, which is less than 1, which is absolutely convergent again. By the root test. Okay. This one says use any test to determine, so now they're leaving it up to us to determine which test to use. As you can see, the entire term is raised to the nth power, so the root test makes the most sense. So let's apply the root test. Okay, so when you cancel these out, the problem here is that you have 1 minus n, and as n gets larger and larger, these are going to become negative, but the absolute value means that we need positive values. So what you can do to fix that is reverse these two terms, and that will allow us to take this out of the absolute value sign. So in other words, this will become the limit as n approaches infinity of n minus 1 instead of 1 minus n, because once again, because as n gets larger, you want these to be positive because of the absolute value. And that's what this will do. It will make the values positive. And the bottom, since it's not a subtraction, you can just keep it the same. All right, if you divide everything by n, you're going to get limit as n approaches infinity of 1 minus 1 over n, 2 over n plus 3. These terms go to 0, and you'll get 1/3, which is less than 1, which means it's absolutely convergent. Once again, if it's less than 1, it's absolutely convergent, which means it's convergent. By the root test. We always need to state which test we're using. Okay, this one we're not going to use a root test because there's no exponents of n involved. So actually this is going to be a comparison test. So let's check to see if it's absolutely convergent, which we can do by taking the absolute value. Well, we know that this is going to be less than or equal to 1 over 1 plus n radical n, because this can never be bigger than 1. So therefore it's bounded by 1. All right, and we know that this is less than 1 over n to the 3/2, because if the denominator is smaller here than it is here, so therefore that makes this fraction bigger than this fraction. And this is equal to 3 exponent 3 to the 3/2. Okay, and since the series of 1 over n to the 3/2 converges, it's a p-series with p equal to 3 over 2, which is greater than 1. That makes it convergent. Then the series, the original series that we started off with, must also converge by the comparison test. You can just say by comparison. So that is it.